This is lecture 11.3, Discrete and Fast Fourier Transforms. Modern measurement systems primarily construct spectra by sampling an analog electronic signal y of t to yield the sample sequence yn and perform a discrete Fourier transform, for which we will now look at the definition. The discrete Fourier transform, or DFT, of a sample sequence, yn, of a length n is ym, where m is an integer here, and ym is constructed with this sum. This should look somewhat analogous to the integral for the Fourier transform, but it is defined for a discrete series of a signal instead of a functional form, which the integral requires. So we're used to this where we'll have a continuous definition of some quantity or other, in this case the Fourier transform, that has an integral in it, and then on the discrete side we'll have a sum. So whenever you look at the discrete version of it, the definition is usually a sum. So integrals in continuous processes become sums in discrete processes. So it's a familiar theme that I think you've probably all seen to some extent. Then we also have an inverse discrete Fourier transform, which reconstructs the original sequence for these n. So y sub n is another sum where we sum up the transformed samples in this with this complex exponential, and we get out the inverse discrete Fourier transform. It's much more frequently the case that we need the discrete Fourier transform than the inverse discrete Fourier transform, because typically we have a time domain signal that we've measured. We would like to find the frequency domain representation of that time domain signal. The DFT ym has a frequency interval equal to the sampling frequency omega s over n, and the inverse discrete Fourier transform has time interval equal to the sampling time t. The first, n over 2 plus 1, so about half of the DFT values correspond to the frequencies 0, so the DC frequency, all the way up to the sampling frequency over 2. And the remaining about half, one less than half, corresponding to frequencies, the negative frequencies. So the leftmost one is typically negative omega s over 2, all the way to the rightmost, which is negative omega s over n. In practice, the definitions of the DFT and IDFT are not the most efficient methods of computation. We virtually never actually use these two definitions to compute these two values. A clever algorithm called the fast Fourier transform, FFT, computes the DFT much more efficiently. Although it is a good exercise to roll our own FFT, as it always is a good exercise to roll our own anything, in this lecture we will use SciPy's built-in FFT algorithm loaded with the following commands. We're going to use Python for this. There's an equivalent version of this in MATLAB as well. I thought I'd show you the Python way to do it here in this example. Now, given a time series array y representing yi, the discrete Fourier transform using the FFT algorithm can be computed with the following command, just FFT of y. In the following example, we will apply this method of computing the DFT. So, example 11.3-1. We would like to compute the DFT of a sample sequence yn generated by sampling a spaced out sawtooth. We're familiar with the sawtooth wave, which ramps up, drops down, ramps up, drops down. We're going to space out our saw teeth, and look at the spectrum of that signal. Of course, typically we wouldn't construct a signal and then do its discrete transform. Often we would be taking a measurement of a signal, have the time domain measurement, and then convert that to the frequency domain. But we'll construct a sawtooth and then look at its spectrum using the DFT in this example. So we'll use SciPy and NumPy and Matplotlib for making plots. We define several control quantities for the spaced sawtooth signal. So the frequency of the signal will be 12. This is in standard SI units here, so it will be 12 hertz. We'll have 3 spaces between sawtooth. So we'll have a sawtooth, then 1, 2, 3 spaces. At the end, I'll open up the Jupyter notebook in which I write my Python code, and we'll change this and just see what all changes when we do that. So we'll have a sawtooth, and then we'll have 3 spaces, and then we'll have another sawtooth. We're going to generate a signal with 10 periods in it. The more periods you have, the better your spectrum estimate will be. Of course, when you're measuring something, the more samples you have of something, the better your estimate is of the signal. So we'll do 10 in this case, 10 periods of the signal. So the sawtooth period would be ramp up, go down, then in this case 1, 2, 3 counts of space, and then we'll go ramp up again. And then we'll have 10 samples per sawtooth, which will also mean 10 samples per space that we put in as well. These quantities imply derived quantities that follow. So number of sample periods with the number of sawtooth samples times 1 plus the number of spaces. So 1 being the sawtooth and the spaces being the other counts that we'll have with the signal at 0. Total number of samples then is going to be the number of periods times the number of samples per period, which is what we've calculated in the line above. The period of the signal will be the 1 over the frequency of the signal. The time array that we'll use is going to be 0 linearly spaced values from 0 to number of periods times the time of the signal, total, the period of the signal, I should say, and then the total number of samples being the number of points we'll take in the lin space. Our delta t then is given in this row, in this line here. It's pretty easy to compute this. This should be equal to the difference between one time array value and the next. There's a little gotcha here. You got to make sure that you do the -1 to avoid what's called the fence post error, which can kind of bite you if you're not careful. And then the sample frequency is 1 over the sample time. We want an interval of ramp followed by an interval of space, or zeros. The following method of generating the sampled signal y helps us avoid leakage, which will be described at the end of the example. So at the very end, we'll talk about what leakage means. So what we'll do is we'll generate zeros the size of the sawtooth. Then we'll generate a ramp the size of the sawtooth, and then what we're going to do is initialize our time sequence for y, and for each period we'll put in a ramp, and then we'll put in spaces depending on the number of spaces we've got. So if you've got 1 space, there'll be 1 space in there. If you've got 2 spaces, you'll have 2 spaces in there, and that's controlled by the spaces variable here. Okay, so we'll plot this here. Just using pretty straightforward matplotlib functions. So plot is the function that actually plots it, and we see that we have sawtooth followed by 3 spaces, so 1, 2, 3, and then another sawtooth followed by 3 spaces, etc. And we have 10 periods total, just like we designed it to have. Okay, so now we have a nice time sequence on which we can perform our discrete Fourier transform. It's enough to compute, or it's easy enough to compute the FFT, so it's simply the FFT algorithm, and if you want the proper normalization, you have to divide that result by the number of samples. So that's what we do here. Recall that the latter values correspond to negative frequencies. Remember that the standard DFT formula gives you the zero frequency and then the positive frequencies and then the negative frequencies after that in the index. This will have a similar syntax. So actually in SciPy they use the same convention in terms of which frequencies correspond to which indices. So what we'll do here is we'll just essentially reorder things so that we have the negative then the positive, so that we can do our plot relatively easily. So kind of annoying, but c'est la vie, right? Now all we need is a corresponding frequency array. So we can compute that, which is pretty straightforward to do. Then the plot created with the following code is shown in 11.14. So once again, we'll plot it. In this case, we're just going to do the magnitude spectrum. We could do the magnitude and phase spectra. We could do the real and imaginary spectra, but in this case, we went with the magnitude spectra. And this is the spectrum that we get, negative and positive frequencies. One of the things we can see here is that low frequencies are pretty significant in this, and then we have this drop off here in magnitude. There's a little bit of a sort of wiggle that happens. And if we were to increase the sample rate, we would actually see our spectrum, our lines would get closer and closer here, because the sample frequency is actually what governs how close these DFT values are in frequency. So not too bad. Sort of runs you through how to do that. Leakage is something that I mentioned above in terms of how we constructed our signal. Typically we can't construct our signal so carefully. We usually are going to be doing a DFT on a measurement signal, which is just something that we're measuring in time for however long we can. The longer the better, the higher the sample rate the better. The DFT assumes the sequence is periodic with period n. So that means that we're assuming that we can repeat the sequence yn over and over again, and that we'll have a periodic signal. So that means that you have a time series. If you've measured something with 1,000 periods in it, the sort of effects of not ending at a clean break of your period is pretty minimal. But if you are only taking a few sample periods, then if you end not in the middle, this algorithm is not going to, it's going to have some effects that will be problematic. So an implication of this is that if any periodic components have period, if it's n short less than n, unless n is divisible by n short, spurious components will appear in yn. So it's another issue. Avoiding leakage is difficult in practice because we're often not able to stop our sample or trim our sample to be perfectly in line with one of these periods or one of these frequencies. Instead, typically we use a window function to mitigate its effects. Effectively, windowing functions such as Bartlett, Hanning, and Hamming windows multiply the time sequence by a function that tapers to 0 near the edges, or to small values near the edges of the sample sequence. What this does is it says, okay, the ends aren't as important, we'll essentially create this periodicity by multiplying the center of our signal by something that's close to 1, and then it'll taper off towards the edges, and those edge sample periods will be less important. So let's plot these window functions to get a feel for them. We'll do Bartlett, Hanning, and Hamming, which are all available in SciPy. And this is what we see. So Bartlett's just a simple triangle. Hanning is smooth and it tapers to 0. I'd say this is probably one of the more popular ones, the Hanning. And then the Hamming is also pretty nice, which is also smooth, but it doesn't go to 0 at the edges, which is kind of a, if you're feeling pretty good about all of those edges of your data, you might want to do Hamming. If you're not as confident in those edges, you might want to do Hanning, because it takes those to 0. So these will minimize leakage, and those artifacts won't be as significant in your Fourier transform data, your discrete Fourier transformed data. So that's all I've got for this. Yeah, if you have any more questions. Oh, I wanted to look at the, I wanted to show you guys, we could play with this. So here's the source for the PDF that you guys are looking at. Say we change the space from 3 spaces down to 1 space between the sawteeth. Recompute everything here. This is what the signal looks like now. There's only 1 space in between instead of 2. Now we'll look at, so this was our old spectrum. Our new spectrum looks like that. So what we've got are essentially further spaced out frequency spikes, and that spectrum is of course slightly different, but overall characteristics are the same. You can continue to play with this, so feel free to play with this code and come up with your own spectra. I was gonna see, let's see, if we change the frequency of the signal to like, I don't know, 48. Okay, now pay attention to the frequency axis here. We went from a small frequency, this is the old one, to much higher frequencies. So these are spaced out more in frequency, right? We got a wider spectrum because we had a higher frequency signal, and we saw we see that we actually get more estimate of our spectrum this way. So it's another variable you can play with and look at how the spectrum changes. So you could also add noise onto this, which would be interesting, which would be a little bit better estimate of, well, it would be a little bit better, I guess, simulation of what you would get from a measured sawtooth that was spaced out, which would be more frequently the type of situation that we have, which is a measurement signal with noise on it, and we would get to see the spectrum with the noise in it as well. So, okay, that's all I've got for this.